with a slope of 1 and a y-intercept of 0. Cuts through quadrants 1 and 3 right down the middle. Okay, it's our parent function, it's our starting point. Any type of transformation that we do to it, like we talked about in Mod 4, is going to change where this line is and how this line looks, okay? So if g of x now is the quantity of x minus 3 plus 1, that tells me that I'm going 3 units to the right. Right inside the parentheses, we're talking about left to right. And we got to think in terms of opposites. So if you see a minus 3, you're actually going to the right. But this little plus 1 on the end tells me I'm going 1 unit up. So when we don't have any sort of vertical stretch or compression, when we don't have an a value in front, it's really, really simple because we're not changing the slope of our line at all. Okay? What we want to do is we want to take 2 points. I'm going to go with my y-intercept and just some other point on the line. Obviously a point that cuts the coordinate plane perfectly. And I'm just going to translate each of those points 3 units to the right and 1 unit up. So if I'm here at this point, I'm going to go 3 units to the right, 1 unit up, and make a dot. Over here, I'm going to go 3 units to the right, 1 unit up, and I'm going to make a dot. Now, I can clearly see that, because we didn't stretch or compress this function at all, and I have a slope of 1, that I'm going to have a bunch of points all along this line. So that means I'm going to have a bunch of points all along my new line as well. Okay, once we get as many points as we can, remember you always want as many points that can fit. You just connect them up. And here now is my line for g of x in pink. Okay, another way that we could go about doing this is just by simplifying into slope-intercept form. Okay, if we break down those parentheses, there's nothing that we're distributing, so we don't really need those parentheses there. If I just get rid of the parentheses, I have what? I have g of x is equal to x minus 3 plus 1. Okay, I can combine these like terms, and this is just another word for y. So this turns into y is equal to x minus 2. All right. If y is equal to x minus 2, I know that my m is 1, my b is negative 2. I can plot my y-intercept at negative 2, which conveniently we already have a point at. And then I can use my slope to rise 1, run 1, make a dot. Rise 1, run 1, make a dot. All the way up my graph and all the way down my graph. All right. So specifically when we don't have an a value, when there's no stretch and there's no compression, these two translation numbers here, the h and the k, we could just combine them together, okay? Because what this function here says, it's like, okay, I'm taking my parent function and I'm going down 2. Well, that is exactly what we did. We took this line, we dropped the y-intercept down 2 spaces, but my slope stays the same. All right? It's the same as going to the right 3 and up 1, because that's just a different point on that same line. So when we don't have an a value, when we don't have any sort of reflection, a minus sign in front of my a value, the transformation is a lot easier. Okay? But if we do have an a value, it makes our lives a little bit harder. Okay, my parent function hasn't changed. That's why they're the same graph. Because f of x is equal to x. It's always going to be my parent function until it's not. And this g of x is loaded up. We got a lot of things we're doing. We got all 4 transformations. We're reflecting over the x. We're vertically stretching it by a scale factor of 2. We're translating 1 unit to the left. And we're translating 2 units down. Now that's a lot. Up here we just had 2 little things. So it wasn't hard for us to do those 2 things and make our line. But here, because there's so much to do, and especially because we have an a value, right, that number in front, the easiest thing for us to do is just simplify. We know how to write equations in slope-intercept form, and we know the shortcut to graphing an equation in slope-intercept form. So let's just put this in slope-intercept form. All right. To do that, I'm going to distribute the -2 to my x and my h. I'm going to change g of x to just y. And this becomes y is equal to -2x minus 2 minus 2. Right, I still got that k value on the end. Okay, -2 minus 2. Again, if I combine like terms, this just becomes y is equal to -2x minus 4. Okay, where my m is -2 over 1. My b is -4. It's a lot easier for us to just graph it that way, as opposed to taking this parent function, going 1 left, going 2 down, and then changing our slope to -2 over 1, -2 over 1. Okay, if you don't remember how to graph a linear function in slope-intercept form, go back to September 30th, 4.1a. Again, we have step-by-step instructions on how to do that. All right. So if my b value is -4, I'm going to go down to -4 and make my first dot. I'm going to rise 2 spaces down and run 1 unit to the right, down 2, right 1. Can't go any further, so I'm going to flip it around. I'm going to go up 2, left 1, up 2, left 1, up 2, left 1, boom, boom. And there's my line for g of x. We started out with the same parent function, f of x is equal to x, but because we did so many things to it, our line looks a lot different. It's much steeper, it's sloping in the opposite direction, and it's been translated left and down. Okay, you could also graph it using the intercepts. If I want to find the y-intercept, I just cover up my x, y is equal to -4. Boom, there's my y-intercept, y equals -4. If I want to find my x-intercept, I set this equal to 0. I add 4 and divide by -2. Gives me x equals -2. Boom, there's my x-intercept right there. That's going to be on the test too, right?